Hello, welcome back. I'm Jason. Today we're going to take potassium metal, we're going to drop it in water, watch the chemical reaction, the fire and the explosion that happens as a result. We'll film it in slow motion and try to learn as much as we can from it. Do not try this at home. This is something you do not do yourself. Let me do it with my safety equipment. Let me take the risk filming everything so that you can learn from it, so that you can learn from the situation without having to do it yourself, because this stuff is explosive. When you put it in water, it basically explodes. And so I do a tiny amount with lots of safety precautions so that you don't have to do it yourself. Let's take a look at it in slow motion and we'll go from there. Now, as you look at the slow motion video, I want to call your attention to this beaker of ordinary water. I want to ask you to have this concept in your mind as we look at the slow motion video. This is aluminum foil. It's aluminum metal. If I take this liquid water and drop the aluminum foil in, absolutely nothing happens. Of course, the aluminum floats on the surface there because I've got it in the proper shape for the buoyancy and all that stuff, but no chemical reaction is happening. Aluminum is a metal. Copper, if I put it in there, nothing will happen. It's a metal. Nickel, iron, I put it in water, nothing happens. They're all metals. What is so special about this potassium so that when I put it in water, it causes fire and explosion to happen? Why? So that's what we're going to do today. Let's go look at the slow motion, and then we're going to talk about the science of exactly why it happens.
Now, I wanted to give you a feel for how fast this reaction happens. This is actually for sodium, and you can see the explosion happens almost instantly. Here's a slow motion shot with a single drop of water. Notice how the potassium reacts almost immediately. In just a second, we'll compare it directly to sodium, and sodium reacts very violently as well, but potassium is even more reactive. The reaction goes from very gentle to instantaneously crazy, for lack of a better word, very, very, very fast. And in fact, the whole thing begins to melt into a molten ball of potassium pretty quickly because the melting point of potassium is actually even lower than sodium, so it doesn't take much to melt it. And it turns into sort of like a puddle of goo, for lack of a better word. Really, it's a puddle of molten potassium very, very rapidly. And it's bubbling because it's producing hydrogen gas. Some of it may be igniting and very difficult to see, or maybe if the temperature is not hot enough, maybe it hasn't ignited and caught on fire yet. Here, I want you to pay special attention to how fast it begins to react, and we'll see that it's even faster than in the case of sodium, and also how fast it goes from a solid to a liquid molten state, again, much faster than in the case of sodium. It basically goes from nothing at all to full-on molten reaction almost immediately. Here's a direct comparison between potassium on the left and sodium on the right. You'll see the potassium reacts immediately. It starts to melt. It's consumed in fumes and reaction products immediately and is much more reactive than sodium. Now here is a test tube. I'm dropping some potassium into the water. You'll see that it begins to react immediately and starts to produce hydrogen gas. And when I speed up time a little bit, you'll see in real time how fast it's actually producing a lot of hydrogen gas. If that gas is burning down there, which is possible, then it's with a transparent flame because I couldn't pick it up on the camera. Eventually it reaches a critical point and then it begins to explode and shoot the molten potassium out of the end of the test tube. And if you look closely, you can see that those molten bits are glowing, yellowish, kind of like amber colored, and it's over in a second. Here's a close-up of the potassium entering the water. You can see that it begins to react almost immediately, violently producing hydrogen gas in the tube. And then when we get a little bit farther down the line, the explosion happens almost immediately, even at over 1400 frames per second. It spews the molten potassium up the test tube. It's very sudden and it's very, very violent. Here's a close-up of the end. You can see all of the shrapnel coming out. If you look closely, you'll see molten bits of potassium that are glowing like a pale amber or a pale violet in color. And if you look, the smoke itself is really cool with the vortices and the rotational motion as it goes off of the top edge of the frame there. As a point of comparison, here's sodium doing the same thing. You can see that for sodium, the explosion is bright orange, almost yellow, and all of the shrapnel is also glowing in that same orangish glow. That's because of the atomic transitions in sodium are just brighter and orange. Here's potassium dropped straight into a beaker. Something cool happened that I did not notice until editing the video. The hydrogen is formed, there's a bubble. Look at that bubble. Look at that mushroom cloud, and then boom, it ignites with a pale purplish glow flame. Now here is a close-up of that bubble forming, the mushroom cloud, and then boom, ignition. Again, pale and difficult to see with the naked eye and with the camera. Fast forward maybe half a second into the future, finally the explosion happens and you can see the shrapnel flying with the molten bits of potassium, again, glowing with that pale, it's not really orange, it's more of a purple or violet color. It's quite a beautiful color actually. Here's a wide shot of the explosion and actually why potassium is so dangerous, because when the explosion happens, you see that's not even it yet. The main explosion's right now. It's shooting up several feet into the air and you can see that this amount of potassium is very, very small. So from here on out, I was on a quest to try to capture that beautiful flame a little bit better. Here's potassium in a shallow beaker with the explosion, and there's almost like a secondary explosion afterwards that has more molten material. I think I'm going to push in and zoom in a little bit tighter in that second shot so we can see it better. What I love about this is you can kind of see two explosions. There's the first one, then there's a bubble that ignites and then forces the second explosion up with even more molten material. And you can see these fragments flying with that pale violet flame. The more I think about it, I think the potassium color of the flame is much more beautiful with greens here. You can see a little green and also that purple, whereas the sodium is brighter and more impressive looking because it's so bright. When you look closely here, for the first time I can see not only the violet but a distinct greenish, almost like an aqua flame here. And it gets more and more intense and more irregular, and then suddenly out of nowhere the explosion happens and then again shoots water and shrapnel up into the air. You know, just to geek out with you for a second, with the water, you can see the reflection of my three big studio lights for this slow motion work. Each of them is 900 watts. So there's a lot of photons hitting this stuff in order to make these slow motion shots possible. Well, I finally got the shot I'm looking for. I really wanted to get that flame by turning down the studio lights. And you can see the ignition happen almost immediately. It isn't orange, but it's a little bit violet, a little bit of tinge of green there. And this is the take that just keeps on giving, because here the potassium is obviously burning with the hydrogen gas and also exciting the vaporized potassium that's going above, and the electron transitions giving us all the colors. But as it scoots around the surface of the water, it just continues to give this amazing light show. It's almost like some kind of like solar flare coming off of the sun. You can see the surface of the potassium bubbling and roiling. Obviously it's totally molten now because it's a sphere. And then you can see the flames kind of like shooting off of it and kind of like geysers erupting and then going into more excited times when it's just shooting material off violently in all directions. And then other times it's a little bit more quiescent and getting ready for like the big finale there. Now this is incredible. Look at the symmetry here in this explosion, just a cone of material in all different directions. And then it quiets down, getting ready for the grand finale. You know, that's what I love about the potassium. There's usually multiple explosions in each event, whereas the sodium seems to all go off at once. Notice how there was just 2 explosions in rapid succession there. It's quite beautiful on a small scale. I only wish I could get more of it and focus at any one time. It's difficult to do, but I think the shots turned out pretty well. Now it's hard to top that, but by turning down the studio lights, I was able to see the flame a little bit more clearly and vibrantly. And so here's another really impressive explosion that just seems to send a shockwave and sort of like a cone of material up and fanning out at about 45 degrees in each direction. It's over almost immediately by the naked eye, but it's quite beautiful to see in slow motion. I almost didn't include this shot, but I went ahead and included it because it was the clearest image I had with the studio lights down of that beautiful green flame that glows with that vaporized potassium there with the electronic transition. So you could see Right before the explosion, it gets very, very intense, very green, almost aqua, along with these pale violet colors. And then it's accompanied, of course, with the grand finale explosion, sending those colors in all different directions. Now I wanted to show you what potassium looks like up close. It's a very soft metal. You can cut it with a knife or even with your fingers. Notice how shiny it is. Right after you cut it, it's shiny, but it reacts almost immediately with the water in the air, turning it a much more dull color. And also it's bubbling there. It's reacting with the water vapor in the air, producing hydrogen. And in fact, if you put water on it in real time, the reaction is over almost immediately and turns into like a puddle of goo. Well, it's really potassium hydroxide and water, but you get my meaning.
All right, now what we want to do is not just look at the pretty pictures. I think we all can see that they're very impressive looking, right? And very awesome, very incredible looking, that a reaction like that happens upon contact with no like ignition source or flame or lighter or whatever, just happens spontaneously. So I want to explain it. And the easiest way to explain it is to look right above potassium on the periodic table. Potassium is right below the element sodium, and I've already done the same experiment with sodium. So I did sodium and potassium right next to each other so that I could see the differences and the similarities between them. All right, and so what I've already done is I've constructed a lecture to describe exactly why sodium behaves similarly. Sodium and potassium behave similarly. They violently react with water, but potassium is a lot more reactive. So what I'd like to do is recap the lecture that I've done for the sodium so that you understand why the sodium is reactive, which will help us then understand why the potassium is even more reactive. So let's do that right now. So sodium, as I mentioned before, is right here in the periodic table. It's element number 11, and it's in the first column. These are highly reactive elements, but you might ask yourself, why are they highly reactive? That's what we're going to talk about today. Basically, what you're taught in chemistry is that everything on this side of the periodic table wants to lose an electron. In particular, everything in this column wants to lose a single electron, and you're taught that it's doing that to try to look like the nearest neighbor over. If it loses an electron, it looks like neon, which is has only 10 electrons. Here we have 11 electrons, so it loses one, and it looks like neon. And you're taught that elements like to do that. They like to lose or gain electrons to look like the noble gases. We're going to talk about why that happens here, but that's what's happening in a big picture. It wants to lose that electron. All right, but water, as you know, is H2O. There are two hydrogens bound up with a single oxygen. And the way the molecule really looks is a bent molecule where the two hydrogens are actually on both sides of the oxygen, and it's not in a straight line, it's bent like this. So what happens is, because the sodium wants to lose an electron, then what happens is these hydrogens want to gain an electron, and once they grab the electron from the sodium, they can detach from the water, and the hydrogen becomes free. And the hydrogen can then bond together with another hydrogen and make H2 gas, and then that gas is very hot from the reaction, and because hydrogen is combustible, then it catches on fire. And then often an explosion follows, right? And then it's so hot that the sodium metal itself, it gets molten into a ball, and you can get a splattering of this molten metal, which is really dangerous. You can really, really hurt yourself. And so you have to be very, very careful about that. All right. Now, when you burn hydrogen, what does the flame look like? Well, in the videos, you could see a lot of orange. And so, but actually, when you burn hydrogen, if you look at the space shuttle, the fuel from those main engines at the bottom was hydrogen, and the oxidizer was oxygen. And when it burns, it makes this pale blue flame. So blue is the color of hydrogen that's burning, and you can see a little bit of blue in some of the slow motion videos that I have. But you see a lot of orange also. So what's going on there is that the hydrogen is burning almost colorlessly, and it's getting the sodium hot, and so it's melting into a ball, right? And that ball skips around the surface. You saw that many, many times, right? But eventually the sodium vaporizes because it goes from a solid into a liquid, and then it goes into a gas, and it's floating in as sodium vapor, basically. And there's 11 electrons around sodium, and so there's a lot of electrons that can jump up and down in the energy levels. And sodium has a characteristic yellowish orange glow when the electrons are excited and jumping around. In fact, there are lights that are made in stadiums, like big stadium seating, and it's called sodium lights because it makes that nice warm yellowish kind of light that we like to see a lot of times. So sodium glows orange, and that's why we saw so many orange flames of orange flying off there. It's not necessarily that the sodium is burning, it's just it's molten, and a lot of times it's vapor, and the electrons are jumping around and making that nice orange glow. All right, and then eventually the entire concoction explodes. And that's another thing I want to get to a little bit later. Why does the explosion happen? Is it hydrogen building up underneath into a pocket and then boom, it explodes? Is it some other mechanism? Is it water vaporizing and, and then causing it to fly everywhere? Is it the sodium vaporizing really rapidly? What is it? I'm going to save that for a little bit later in the discussion. But the finale is the thing explodes and then you see all the chunks going everywhere. All right, so that's the recap of what's going on. Sodium wants to lose an electron. When you put it in water, you have these hydrogens who want to gain an electron that are able to pull on it and grab that electron. And when that happens, this, that's my sound effect, this hydrogen pops off, and then it's a free agent to go combust with oxygen or to bond with another hydrogen and then combust. And then when that heat happens, then it makes everything hot, the sodium gets molten, and then vaporizes and eventually explodes. That's the top level discussion of exactly what's happening. But as in science, you should never just, you can go down a rabbit hole. Any science question I give you, if I say, why is this pen black? You'll say, well, it's black because it's got black ink. But then you could go a level deeper. Why is the ink black? Well, because it absorbs a lot of all the colors of the rainbow from the sun or from the lights, and it doesn't reflect much, so that's why it's black. But then you can go a level deeper and you can say, okay, but why does it absorb those colors? Well, that's because of the pigment in there and the electrons. And you could say, okay, well, why are the electrons in that way absorbing all those wavelengths? And then you could go down and down and down. You see what I'm saying? Eventually you get to quantum mechanics. All roads lead to quantum mechanics when it comes to matter, right? So for this, we could say a top level, sodium wants to lose an electron to look like neon, but then you have to say why. Right? And I just told you the hydrogens want to grab the electron and pop off and then burn. But then you can say why? Why does the hydrogen want to do that? Why doesn't it just stay bonded to the oxygen? Why doesn't the water just stay together? Why does it pop off at all? Why does that happen for sodium? But then when I put the aluminum foil, which is also a metal, the electrons in this foil are not being attracted to the hydrogens. They're not popping off. They're not causing a reaction. If I put copper, nickel, any other common metal, nothing will happen, but only with these first column guys right here. Why is that the case? That's what we're going to get to next. So stick around. We're going to talk about that. Okay. First of all, to read this thing, this periodic table, sodium has 11 right here. That means there's 11 protons in the nucleus. So what we basically know is that for sodium, which is element 11, there's 11 protons in the nucleus. And if you look it up in the periodic table, you'll find that there's actually 12 neutrons. Again, these are both in the nucleus. So I'll even put something here, nucleus. Right? And then over here, we have 11 electrons surrounding everything. So I'm going to say in orbitals. So you're quickly going to figure out that the model that you were taught of an atom when you were in like 5th grade is just wrong. And in fact, it's wrong for me too. I don't know what an atom looks like. Nobody does. We have models. We have models that seem to agree with experiments. But all of our mental models are always wrong. So anybody that tells you they know what an atom looks like is wrong. I will tell them to their face they are wrong because nobody knows what an atom actually looks like. But we have really good models. But it's definitely not little balls of electrons going around like a solar system. It's not like that. Okay? These electrons exist as probability clouds around the nucleus. And they exist at different distances from the nucleus, and they exist in different shapes. And that's the weird part about it. Right? Sometimes an electron can exist in a wave-like state that's a spherical kind of shape to it. And sometimes electrons exist around the nucleus in kind of like a dumbbell shape where it's like lobed on the top and lobed on the bottom. I'll draw a picture in a second, right? And they're more complicated shapes. The higher you go in the periodic table past these initial elements down way in here, there's 47 electrons in silver. Some of those electrons near the end have funky shapes. And when I say shapes, you're thinking, what do you mean by shapes? Electrons are little balls. They're not balls. You were lied to, right? Because we don't have good mental pictures. They exist as wave-like structures with complex shapes. And the wave-like structures represent the probability of finding the electron when we measure it. Sometimes the probability cloud is a sphere. which means that all the way around it may have the similar probability. Sometimes it's a lobe structure, which means it's more likely to exist on the top or the bottom when you measure it. Sometimes it has these crazy shapes that I could draw all day when you get up here, these crazy F orbitals and things. They look very beautiful, but they're these lobe structures that look very weird, right? And that is going to be critical to understanding why sodium wants to lose that electron. Now, in order to go any farther, we can't just say sodium has 11 electrons. We have to talk about what's called the electron configuration. We have to talk about how are the electrons arranged around the atom. Yeah, we could just say there's 11 of them, but it doesn't tell us anything. How are they arranged? Because it governs the details of why it does what it does, which is where we're trying to go. So here, I'm going to draw something that might scare some of you, but I promise you, if you just can turn off your scared part of your brain and just absorb what I'm telling you, you will open your mind and you will understand. It will not be hard. But we're going to talk about the electron configuration. So let me write this down with a color that works. Okay, so electron config. Okay, and this basically tells you the shapes of all these things that are existing around there. Now for sodium, it looks like this. I'm going to draw some stuff, and then you're going to be like, what is he talking about? Just let me get through it. I promise I'll make it clear. The first couple of electrons, there's 11 electrons total. The first couple are very close to the nucleus. They're in the first energy level, that means number 1, closest to the nucleus, and they're in an s orbital. S stands for spherical, right? And the 2 here is not like algebra. It's not s squared. The 2 means there's 2 of them there. So there's 2 electrons that can exist in the shape of an S spherical nature in the first energy level, which means the one that's closest. You can kind of think of it like Mercury in the solar system. It's the one that's closest. There's a minimum energy level. It can't be any closer than that. Now, I'm oversimplifying already because you're already thinking spherical. Oh, it's a shell. Well, actually, it's a spherical thing that extends throughout space forever according to a mathematical formula. I'm not giving you all of the details because otherwise I'll put you to sleep. Okay, you got to start somewhere. So think of it as a spherical thing, but just know that when you look at the equation, it extends as a sphere with decreasing probability in all directions forever. Okay, but it's at it initially kind of starts at some maximum maximum probability distance from the nucleus. Okay, but that's only 2 electrons. But there's a lot more, right? There's like 9 more for a total of 11. All right, so then you have the next 2 electrons exist in the second energy level, again in an s orbital, and only 2 of them can fit there. So this s orbital, the spherical nature, anytime you see an s, it can only hold 2 electrons. That comes down to how we figured this stuff out to begin with. You've heard of quantum mechanics, the Schrodinger equation. When you solve that equation, the solutions come out to tell us that these electrons in the spherical state can only be 2 at a time. Once you have 2 of them there, then they have to go to another state farther away. So this one is farther away. It's in the second energy level, a little bit farther away. You can think of it as a spherical shell farther away from the first 2 electrons. So this is a total of 4, but we have more on the way. After you fill up these 2 electrons in that spherical shape, you're still in the second energy level, the big 2, but you're not in a spherical state anymore. They go and exist in what's called a p orbital, and there's 6 of them right there. Now the p orbitals are, I'm already compressing a lot of information. The s orbitals, I will say, are spherical. I'll draw a little circle here to remind you that these are spherical, but the p orbitals exist as these dumbbell shapes, right? Now I'm only drawing top and bottom, and each of these can hold 2, so there's 2, but there's another p orbital sideways for 2 more, and there's another p orbital coming out of the board for 2 more. So each of the p states, up, down, left, right, and into and out of, can hold 2, 2, 4, 6. It can hold a total of 6, but I'm only drawing one of them here. But notice the shape is different. That means there's maximal probability of the electron being somewhere in here, but almost no probability of electrons in this state being to the left or to the right. Whereas this was more of a spherical distribution there, okay? You might say, well, how do we know it's a dumbbell shape? Where did that come from? That's what I was telling you with the ink here. We could go another level deeper and we can have a whole hour-long discussion, but it comes from the Schrodinger equation. It's an equation in math. When you solve it for atoms, you get these different shapes. Just like in algebra, when you solve an equation, sometimes for a line, you'll get a single solution. But for a quadratic, like a parabola, you get 2 solutions. And in trigonometry, you might get sine or cosine or tangent for solutions. Those are different functions. Well, for the Schrodinger equation, you get very complex shape that are imaginary wave-like structures. Some of them look spherical and some of them look dumbbell-shaped. And that's where they come from. They come from the Schrodinger equation, right? And so the Schrodinger equation was invented, it was solved, and then we can use these shapes of electron clouds to predict how things will bond and their bond energy. So we're reasonably sure it's correct or very close to correct because it agrees with the experiment. It's not like something some guy just invented, Erwin Schrodinger, he just invented, hey, good job, you did great. No, it's that he invented, solved it, and it agrees with how things bond in real life. How things sometimes don't bond. It predicts things like what we're about to talk about today. Okay, so here we have 6 plus 4. That's only 10 electrons. Sodium actually has 11 electrons. So here is the punchline. The last single electron in sodium is in the 3rd energy level because the S and the P are full, and so when they're full, you go out even farther away to the 3rd energy level. And it's a spherical level. Notice how it always starts spherical, then sometimes there's a P. Anyway, we're there. And there's one single electron left over because remember, sodium has 11 electrons in total. So here's 2, 4, 10, 11. So these are all the electrons in sodium. But notice that this last electron is hanging out here, and it's also in a spherical shape. And I'm going to write one thing down. I'm going to say these electrons that are over here, these are close to nucleus. And these are far from nucleus. You can think of these energy levels being like ladders, like rungs on a ladder. And the higher the number of steps, and the farther away from the ground you're going. In fact, this is actually called the ground state because it kind of is like a ladder. And you can think of this arrow going from this direction to this direction. And as we move through the orbitals, these are kind of closer to the nucleus. These are a little bit farther away, and then these are even farther away. And as we go through the periodic table, past sodium to magnesium, 13, 14, 15, all the way to argon, we're adding more electrons, and those electrons, eventually, as you get through the periodic table, they go into higher and higher energy levels, which means the electrons are physically farther away, or they're a higher probability of being farther away, is the right way to say it. A higher probability of being farther away, the bigger and heavier the atom actually is. So you can kind of think of the solar system. Mercury is really close, even though we know this is not a solar system. Okay, you got to use an analogy. Mercury is really close, and Pluto is really far away. Pluto is very tenuously held by the sun's orbit. I mean, it's in orbit. It is in orbit, but it's much less gravitationally bound to the sun than Mercury because it's so far away. And the same thing is true of this. This single electron on the end, remember I told you the whole thing happens because sodium wants to lose an electron. And what you're taught in chemistry is that this sodium wants to lose an electron to look like neon, but that doesn't give you any intuition because electrons don't want anything. Sodium doesn't want anything. It doesn't have emotions. So we use words like it wants to do this, but it doesn't want anything. It's just losing the electron easily because that last electron's really far away from the nucleus, and it's real easy to poach it and to grab it if something else is tugging on it hard enough. And guess what's tugging on it? The water is tugging on it. I'm going to tell you why that happens in just a second. Okay? So this one's far away. But notice that let's say the atomic nucleus is right here. Let's say the nucleus is over here. And then these electrons are farther and farther and farther, and we have a single electron way over here. So you're way out like by Pluto, and you're looking way down, way in the middle, way over there somewhere is the nucleus. The nucleus is very small and positive. But between you and that positive nucleus, and remember, opposites attract, so I have a negative, and that nucleus is positive, right? Opposites attract. However, in between you and that nucleus is 2 electrons here, 2 electrons here, 6 electrons here, and then I'm way out here. So I don't see the full pull of 11 protons pulling on me in the nucleus. Why? Because the nucleus is way over there, and there's a ton of negative electrons in the way. So we say the nucleus is shielded, kind of. And we say that, yes, there's a positive charge of the nucleus, but this single electron doesn't see the full extent of the positive charge of that nucleus, 11 protons pulling on it, because of all the electrons in the way. If you just add up the 11 positive charges and all these negative charges that are in the way, and you add them up algebraically, you're not, positive plus negative, you can get very close to 0 very quickly. So you're not seeing a full tug of 11 positive charges. You're seeing something way less than that because all of these negative electrons are shielding you. So this thing is not only, weakly held onto because it's far away. it's weakly held onto because it's far away, and it's not even seeing most of the charge. It's not feeling most of the charge of the nucleus because it's shielded by all these electrons in the way, negating the positive charge from the nucleus. That is the punchline as to why everything in this column reacts so readily, because there's a lone electron hanging out way beyond the orbit of Pluto. And that electron is shielded from seeing the positive charge tugging on it from the nucleus. So it's just very easy to pull it off. You do need something to pull on it some, because it is held into the nucleus. It's bound, it's attracted. But if anything is a little bit stronger than that, you can just pull it off. And it turns out that water and lots of other things are very, very easy to pull on that, okay? Okay, so to recap, S orbitals can hold 2 electrons, P's can hold 6. This is a single electron out here. Now, in just a second, I'm going to draw the electron configuration for another really reactive metal on this table called potassium. You know that when you put sodium in water, it reacts violently. And I'm going to do an experiment soon where I drop potassium in water, and we're going to see visually that it reacts even more violently, right? So that's a fact. That's a thing, right? But without even writing the electron configuration, you should have the intuition to know, why is potassium more reactive? I'm telling you ahead of time, it's more reactive. It reacts more violently. It gets hotter. It explodes more violently. Why? Well, if this one happens because of this single electron that's far away, what happens when you add an electron? You add another electron, then another electron, 13, 14, 15, 16, another electron, then it wraps around here. I'm going to write down the electrons in a second. But what I'm going to tell you ahead of time is that when we write it down for potassium, that last electron that's added is going to be on an orbital by itself, just like sodium was, same exact situation, but instead of this many electrons being in the way, it's going to be in a 4s energy level, even farther away, with even more electrons in the middle. So that electron from potassium is going to be held even less. It's going to be held even less strongly, because for potassium, you had to add all those electrons, and finally that last one is, if you think Pluto's far away, how about halfway to the next star system? That's how far away that last electron in potassium is. And because of that, it's looking back to the nucleus really far away, and all of those electrons are in the way. And it's shielded even more from the nucleus, so it's even easier for water to rip the electron off of potassium. So that's what we'll do next. Let's write down the electron configuration of potassium and draw the comparison. So to continue, we now know that sodium has 11 electrons, and all these elements are in between sodium and potassium. Potassium has 19 protons in the nucleus, and so 19 electrons. So we have to write down its electron configuration and see that that is how they are similar, that their electron configurations are similar. That's why they have similar properties. So in order to go that direction, we'll say that potassium, which we just said is going to be more reactive, and I'll do a separate video on that, that has 19 electrons, so a whole lot more than sodium there. Why would having more electrons make it more reactive? Well, we're going to find out right now. All right, so we have to fill up the electron orbitals in the same way, right? First, we start out, the innermost 2 electrons fill up in the same way as what we had here. So let me start over here, 1s2. So that means first energy level closest to the nucleus has 2 electrons in the s spherical orbital. And then the next 2 electrons fill up just like sodium, so 2s2. So a little bit farther away, 2 more electrons go in the spherical orbital. Okay, then we fill up the same way here, 2p6. So 6 electrons are in the dumbbell orbitals. Again, let me just say one thing about this. I have 2 lobes here. It's not like 1 electron's up here and 1's down here. The entire structure, the lobe structure on the top and on the bottom, is a wave-like state. The whole enchilada is a wave-like state. And an electron is a wavy thing that operates, that takes the shape of that. It's called a standing wave. If you ever jiggle a rope against a wall and jiggle it so that you see the standing wave pattern, that's kind of what's happening to the electron waves, okay? That's the best analogy that we have. So it's not like 1 electron here, 1 electron here. It's that an electron is this shape, and 2 of them can be in this shape. There's a difference in something called electron spin and some differences that I don't want to get into in this lesson. But basically 2 of them can fit into this shape, 2 of them in this shape, 2 of them in the shape, the dumbbell shape out of the board. So there's 6 more there. Now, For sodium, we only had one extra electron, so it kind of like ended right here. But for potassium, we have tons of electrons left. So the next ones are going to go into the 3s orbital just like this, but instead of one, there's two of them. Remember, all of the s orbitals can only hold 2 electrons. The p orbitals altogether in the 3 different directions can hold 6. So how many do we have? We have 10 right here, and then 12. So we have a whole lot more electrons to go. So what comes after the 3s orbital? Well, we have to fill the p orbital. It comes next, 3p, and a total of 6 electrons can fit in there. Again, it's the lobe structure, some up and down, some left and right, some in and out of the board. 3 dimensions there, 3 different directions, x, y, and z. So how many do we have now? We have 10 right here, and then we have 8 here, so there's 18, but we have one more electron. So what would come after s and p, after we exhaust the 3p orbital? We have the 4th energy level, and that's going to be an s orbital, and there's only one left over. So you see what the similarity is between potassium and sodium is that the orbitals for the electrons always fill in the same order. It's kind of like, I don't know, it's kind of like pouring cereal into a very tall, like, I don't know, transparent box or something. If you put the cereal in, it always goes to the bottom, and the bottom layer gets full. And then if you pour some more cereal, it goes and sits on top of the bottom layer. And if you keep putting more and more cereal in, it always fills on top. The more cereal you pour into this like column or whatever, or a bowl or whatever you want to think about, it always fills at the bottom first, the ground state, and then it just keeps on adding farther and farther and farther away. The electrons pile in into the closest energy level, which is in an s orbital, and then the next a little farther away s orbital, s, and then the second energy level can have s and p. The first energy level doesn't have a p orbital, it just has an s orbital. So s, s and p, and then s and p again in the third energy level that's even farther away, and then it goes into the 4s orbital. What do you think would happen after the 4s orbital? Well, there's going to be p, and then if you keep going in the elements above that, you get into D's and F's, and we give them letters, but really these letters correspond to different shapes. This looks a little bit like a flower or 2 dumbbells, but they get to much more complex, beautiful looking shapes in 3 dimensions, okay? Standing wave patterns. And the electrons exist as these standing waves. When you measure them, you might see them occupy a certain space, and these beautiful standing wave patterns represent the probability of finding an electron when we measure it. So here, we are going to have a much more higher probability of finding it on the top or on the bottom of the nucleus here, and we're going to have no probability of finding it on the sides for this particular orientation right here. But how many do we have? 6, 7, 8, 9, 10, 11, 12, 18, 19. So there's 19 electrons. But notice, same thing. The very last electron is always just by itself, just like it is up here. This was the 3rd energy level, this is the 4th energy level, but it's a single electron by itself. And that is why it's easy to rip off, because again, looking out from Pluto, way beyond Pluto, into the nucleus, I'm seeing the positive charge of the nucleus holding me, but I'm looking through all of these electrons. If you want to think of them swirling around, you can, but they're standing waves of negative charge cloud in between me and the nucleus. So the nucleus is shielded. So not only am I really far away, even farther away than sodium's outermost electron, but I'm also looking at a nucleus that's even more shielded because I'm looking through even more electrons. And I have a vantage point very far away. So from a distance, the nucleus doesn't look as positive as you would think because it's shielded so much. All of that means that it takes even less energy to pull this outer electron away. Literally, if you could grab these electrons with tweezers and feel how hard it was to yank them off, right, then it would be a harder force pulling here. You would have to pull less with less energy to rip off that outer electron. And that is why, as I will do an experiment in the future, when we put potassium in water, it reacts even more violently than sodium does. It almost explodes on contact. And if you were to go down the periodic table, I doubt I will ever do experiments with rubidium or cesium or any of these. They're so reactive because, look, 37 electrons, 55 electrons, 87 electrons. The outermost electron is always going to be a lone single electron very far away. For something like francium or cesium, it's so reactive, you toss it in water, it basically explodes immediately because everything is happening so fast and so readily. All right, now we have discussed at great length half of the situation. This is what I wish somebody would have taught me in chemistry or physics. Why do this first column, why do they like to lose electrons to look like a noble gas? That is the reason why. All right, now I'm not going to explain it in great detail, but when you go to the other side of the periodic table, you're taught in chemistry that chlorine, fluorine, even oxygen, they like to gain electrons to look like a noble gas over here. They're wanting to do that to gain electrons for a similar reason. I'll have to like draw it all out. I have to put the electron configuration down. Maybe one day I'll do it. But basically, it likes to suck electrons in because of similar attraction to the nucleus. It's just a little different when you write the electron configuration down. You'll see that the nucleus is able to pull electrons in so readily. That's why things like to react with oxygen, fluorine, and chlorine, because they pull electrons in so much. Now, speaking of that, we have to now talk about water, because that's the other angle here. Water, you're taught, is H2O, but that's not very descriptive. Really, you want to think of it as a bent molecule like this. Single oxygen in the middle, 2 hydrogens on the sides. It's bent because of extra electrons that are up here I haven't drawn, pushing the structure down like this. Now, as I mentioned over here, oxygen likes to gain electrons. You're taught that in chemistry. It does it because of electric forces from the nucleus pulling electrons in. Right? And because of that, what you have here is electrons. This line here is a bond, a single bond from oxygen to hydrogen. When you see one of these lines, what it means is a pair of electrons. 2 electrons are being shared equally. Well, equally is a dirty word. I'll tell you in a second why it's not equal. But they're shared ideally equally between the 2 atoms. Hydrogen through this line gets to sort of feel 2 electrons, which is what it wants, and oxygen also has like 2 electrons here hanging out in the middle. You can think of them sort of hanging out in the middle, and this one's hanging out in the middle as well. Now, why it does that, it goes into chemistry, but that's what the lines are. They're shared electrons, shared, and so they're covalently bonded, shared here and shared here. 2 electrons, a pair and a pair. But because oxygen is so readily able to attract electrons for reasons that will be in another lesson, okay? Then what really happens here is it's not evenly shared. The electrons that are shared here are not equidistant here between the oxygen and the hydrogen. They are just pulled a little bit more towards the oxygen. And these electrons here are not equally shared. They're pulled a little bit towards the oxygen here. And so because of that, this oxygen atom has a tiny extra negative charge on it, because the electrons that are here, it's a neutral atom, but they're being pulled closer. And these hydrogens have a tiny positive charge associated with them, because a hydrogen, don't forget, is a single proton and a single electron. When the electrons are pulled away from it, then you start to see the positive nucleus, and it looks like this side of the water molecule is positive. And over here, this hydrogen on this side of the water molecule is a little positive. But the oxygen is very slightly negative. So you may or may not have learned in chemistry that this water that you're drinking it's a charged molecule, but they don't use the word charged molecule. We call it a polar molecule. A polar molecule is just a molecule where, because of the electron sharing, half of the molecule is slightly positive and the other half of the molecule is slightly negative. Now, this fancy symbol here looks like a snake. It's the Greek letter delta. You can kind of practice it. It's a little snake-looking thing, right? It's a Greek letter delta. It's a letter that we use that just means teeny, teeny, tiny. That's all it means. So there's a teeny, teeny, tiny positive charge on the hydrogen here, a teeny, teeny, tiny positive charge of the hydrogen here, and a teeny, tiny negative charge on the oxygen there. So this water that you drink, half of all of the molecules are slightly negative, and the other half of those molecules are slightly positive. So when you drop a bit of sodium into that mixture of this vast ocean of molecules that are half positive, half negative, what's going to happen? The sodium is going to hang over here, and this hydrogen is slightly positive. Positive is going to attract the outermost electron of the sodium. And it's going to attract it so much that that outermost electron of the sodium is going to get ripped off of the sodium, only because water is polar. Only because water is polar. In fact, if you put the sodium in a liquid that's not polar, that's not charged at all, then nothing happens. And that is how this sodium is stored. It's in oil. Oil is not polar. There is no charge nature of oil. Notice it's not exploding, right? The only reason it does anything in water is because water is a polar molecule that's charged half and half, positive, negative. And the positive side of this hydrogen, it rips off the electron. What do you think happens when this happens? That electron goes in and attaches to the hydrogen. And once it has that extra electron, it no longer needs to share over here, so it pops off, like I told you earlier. And this hydrogen atom floats around briefly in solution. Eventually, it comes into contact with another liberated hydrogen atom and bonds and makes H2 gas, because hydrogen likes to bond with itself. Okay? And then it combusts. Why does it combust? Because when this electron from the sodium gets yanked off, it is not a peaceful process. This electron is being attracted by the nucleus of the sodium. When the water rips it off, it literally rips it off, and once it's free of the sodium, then it literally gets attracted and rams itself into the hydrogen right here, and then the hydrogen separates. When it I'm using my hand to convey that it's literally ramming itself into there, and that's a lot of energy imparted to the hydrogen. And that's heat. The heat then causes the combustion to happen with the oxygen in the air. Okay, so and that's why sodium is melting and turning into the molten ball, because the melting point is low, and all of this creates a lot of heat when it happens. There's no flame. There's nothing that needs to happen. It's just because the water has enough of a charge to yank it off. And if you put this thing, potassium or sodium, in mineral oil that's not polar, nothing happens, because there is no attraction with the outer electron there to be able to do anything at all. So, two more things I want to talk about before we close it off. I've described briefly what's going on, but I want to write down the chemical reaction that we actually see. What happens is we have this sodium, which is a solid metal, and then we add it to the water, right, which is a liquid. And what actually forms is the hydrogen pops off, and then the hydrogen combusts and burns. The sodium has lost an electron. So it's an ion, and so the sodium is hanging out dissolved in solution. And what's left over here, whenever you pop off a hydrogen, you have an OH left over. So the sodium is there, and the OH is left behind. This is called sodium hydroxide aqueous solution. And then over here plus the H2, which is the gas. Now, what's going on whenever we write something like this in aqueous solution? What this really is, aqueous solution means that the sodium is floating around as ions, positive ions, because they've lost an electron. And the hydroxide are also floating around as ions, which are negative ions. So they're both essentially dissolved in solution and dissociated, which means they're not connected and bonded to each other. I mean, they're bumping into each other, they're bonding temporarily, and then they're coming back apart again. So they exist as sodium ions in solution and hydroxide. Sodium hydroxide, that's called a base, which is opposite of an acid. You heard of acids? Well, this is a base, opposite of an acid. There. So, I don't want anybody to yell at me, so we need to balance this reaction, right? We have one sodium, that's good. We have one oxygen, that's good. We have two hydrogens, and we have three over here. Now we have to fix that, and this isn't a chemistry class, but the way you fix it is you put a 2 right here, which would make for 2 hydrogens plus 2 more is 4, and I can fix it by putting a 2 in front of this one right here. So now I'll go back and check. I have 4 hydrogens. 2 plus 2 is 4 hydrogens, 2 oxygens, and now I've got 2 sodiums, and I have to fix that with a 2 right here. So this is balanced. You have the same number of atoms on the left and the same number of atoms on the right. So this is what you would read if you just Google it, what happens to sodium and water. And this is a reaction that you would see. But it hides the beauty of what's going on. You don't talk at all about the electrons. What you're taught is that the sodium combines with this, and it makes the gas, and it makes the hydroxide, the sodium hydroxide. But you have no idea, why does that happen? I mean, why doesn't it happen for aluminum? Why don't, when I put aluminum here and combine it with water, it make aluminum hydroxide and hydrogen gas? The reason why is because aluminum, notice on the periodic table, aluminum is over here. So its outermost electron is totally different character than the ones here. Everything in this column has a single outermost electron very far away that can be ripped off. If we write down the electron configuration for for aluminum, the outermost electron is not as easy to pull away. And water doesn't have the force, for lack of a better word, from the charge on the hydrogens here, enough of it to pull them apart. That's why we put it in there, nothing happens. So we put the sodium in the water. The sodium loses an electron. Why? Because the water molecule, the positive side of it, pulls the electron away. That makes a sodium ion, which is dissolved in the water. This hydrogen pops off, combines with other hydrogens and burns, and what's left is a hydroxide, an OH. That's the OH that's here. We call it sodium hydroxide in aqueous solution. The hydrogen, as we've described, comes together and makes H2, but what I haven't shown in this reaction is that this H2 gets hot enough to combust. If you do this experiment in a vacuum chamber where there's no oxygen on the outside environment, which I think I will do one day, right? Then the reaction happens. The sodium, I expect would get molten and do all the stuff, but the combustion wouldn't happen because there's no oxygen for this thing to burn with. I'll do it one day and we'll see, but that's what should happen. Okay, the last thing I want to talk about is the explosion that happens. Now, frequently in science, cool things happen and you think you know why, but there's not always a clear-cut answer. There's a lot of why does it explode? Why doesn't it explode immediately? Why does it take a few seconds to explode? And why does it, boom, happen all like this, okay? So I learned a lot from doing this. Originally, I was thinking that some of the water actually gets trapped inside of the molten bubble of sodium and then vaporizes and then explodes. And I've done some reading in the literature, and that is true that could be partly going on. But the leading theory as to why it actually explodes after a while is because notice that when we put the sodium in, it makes the sodium ions in the water solution. And the sodium ions are all positively charged. And if you get enough sodium ions in water, then they're going to repel each other violently and then cause an explosion to happen. So somehow, whenever you put it in the water, the sodium is coming out off of the chunk you put in there as sodium ions. Some of them get trapped inside of the molten hunk of molten liquid that you have there. When you get enough of them there, then you have a repulsion event, which we call an explosion. There could be something going on with water vapor as well as possible, but that's the leading theory as to why it actually explodes. It's called a Coulomb explosion. Coulomb from charged particles is coulombs of charge. That's what Coulomb comes from there. So as we said, it all comes down to this last electron. There's a single electron in the outermost orbital in both cases for sodium and potassium, but in potassium's case, this outermost electron is farther away. And that's the way this periodic table is organized. Similar properties are for items in the same column. If you look column by column and look at the electron configurations for all of these columns, you will see that the outermost electrons are similarly organized for the columns. That's why it has this weird shape to it. It's because we've organized it by electron configuration. It really should be called the electron configuration table, really. But that's not so, such a great name, right? It's got a scary sounding name. So anyway, that's why. These all have similar properties here. And as you go down, below potassium, rubidium would be more reactive, cesium would be more reactive, and francium would be more reactive. So the only thing I want to really add to the lecture is, we've already said the outermost electron is even easier to pull off there, is I want to write down the reaction so we can see. If you put potassium, which is a solid, and you put it into water, which is a liquid, what's going to happen? It's going to mirror the same thing of what was going on here. But instead of producing sodium hydroxide, it's going to produce potassium hydroxide and hydrogen H2 gas, which will then ignite and burn on fire. And just like before, this potassium hydroxide, this is in what we call, I forgot to write it there, aqueous solution. Aqueous just means that the potassium, it's existing in solution as an ion. And the hydroxide is in solution as an ion. So this is a base. Hydroxide is a base. And so they're oppositely charged. So they're attracted to each other, but they don't stick together. The water is constantly pulling them apart. So they're always in solution like that. But notice the reaction looks the same. Now, the numbers in front are not the same. We have to, balance the reaction, and we balance it the same way. We put a 2 there, and a 2 there, and a 2 there. 2 potassiums, 4 hydrogens. 2 plus 2 is 4. 2 oxygens, 2 oxygens. So it's balanced. But it's basically the same exact chemical reaction. Potassium hydroxide instead of sodium hydroxide. But that means it dissociated and split apart here into ions in solution there. And the other main difference is that the color of the combustion was a little bit different for the potassium. The hydrogen burning itself is always a pale blue, and we see that in both sodium and potassium in the reactions. But when we look at the sodium, you see these orange and flame colors, and for the sodium. And for the potassium, you see a little bit more muted purples and even greens. So what's going on there is, just like for sodium, the potassium, when it gets hot, really, really hot, it vaporizes into like a little bit of a potassium vapor there. And then the electrons are jumping around. But you know, potassium is a lot more electrons, 19 electrons compared to 11 for sodium. A lot more electrons, a lot more different orbitals that they can jump between and emit different wavelengths of light. So whereas sodium is glowing orange because of those are the main transitions in the electrons in the sodium atoms there, the potassium has a lot more electrons, and so a lot of different colors that can come out. So instead of oranges, it's more greens, and it's more a little bit purpley and things like this. I think the potassium reaction looks a little bit prettier. It looks a little more interesting. But the sodium reaction with the bright orange is actually a little more impressive because it's bright and it looks like a flame. It looks like a fireball flying through the sky. So I'd like you to please drop me a line. I wanted to take potassium, put it in water. I wanted to do it myself with my safety precautions so that you don't do it. I do not want anybody to do this. Do not do it. I command you. And just watch me do it. And hopefully get something out of the explanation. It all comes down to the electrons, in chemistry anyway. Always comes down to the electrons. What are they doing? How are they rearranging? The heat that comes about is due to the electrons. The products and the reactants, because of the electrons. The combustion, because of the electrons. The light that we see, it's because of the electrons. I want you to get something out of the lesson and something out of the experiment. Please let me know what you think. Did you like the lesson? Did you like the lecture? Did you like the slow motion? Did you like it at all? Please tell me, because I do read everything. This is Jason signing off. Please stay curious, and I'll see you in the next one.
Learn anything at mathandscience.com.